It's just part of the deal, I guess. You can do more whiteboard drawings in my office if you want to come by. What were we talking about? Discretizing, right? We were talking about discretizing. We made it through talking about this idea originally of going back and figuring out this mathematical model. We make huge simplifications all over the place. We simplify loads, we simplify stress behavior, boundary conditions, right? We had many simplifications that we use all the time, which honestly is not super accurate, but it works for what we're heading towards. We talked about diaphragm stiffness. I think I made Aaron feel like he was doing things wrong, okay? In the end, I'm not right? You're not right. It basically comes down to you have to be comfortable with it, and it has to be defendable, right? In the end, that's what it's all about, okay? It's unfortunate, but that's the world we live in, okay? It is fortunate, though, because if they put too many guidelines and boundaries on everything we did, then we would have no creativity, okay? Even less than what we already have, okay, as engineers, right? So, just note when I'm standing up here and I'm talking about ways in which you can model things, right? You could model it that way if that's what makes you feel comfortable, right? But in the end, it's really up to you. And for you guys going out in the real world to start out, right? I'm sure you go and talk to Scott pretty often, right? Or some of the other guys asking about your model or how you would approach things, or they have examples of it. And those are really just guidelines as to how other people have tackled a problem, feel comfortable about it, and it has set up like a defendable approach, right? Because in the end, we can all get sued, right? We could go to jail, things like that, right? What we do is no game. So, discretizing, this is a huge deal. As I talked about with beams and columns, right? We want to capture the connectivity and the compatibility of members, which creates a adequate load path. But really for beams and columns, typically we only require one element per mathematical model element, right? So if you have one beam in your model, you're going to model one beam in the real world, right? Or our mathematical model, you're going to model one beam in your finite element model, right? Some areas where we're going to want to change some of this. Anyone tell me the difference between P big delta there and P little delta?
1 second, it's kernel delta.
Yep, yeah, so it's intra-element displacement and how that affects internal forces versus inter-element, right? If the whole model displaces, right, how that affects. In the homework, which one of these did we look at? P big delta, right? So P big delta would be, right, if we had a beam column, like we did, kind of, right? So we had a column on the side of the building, maybe it's the one sitting right behind James in Roberts Hall. It gets wind load on it, right? So say it had a uniform load across the entire height of it. It's more or less supported, right, at the top and bottom. The top is a bit more flexible, right? This building can rack and move underneath some lateral force to it, right? So if we looked at the deflected shape of this, it might look something like this, where this was I'm drawing really small for some reason, right? This was the original shape. So we've got, say, a uniform load on this column, okay? The entire building back here, right, has lateral forces on it. And so when this was pushed on, that top node likely displaces, right? It's not perfectly stiff. It's not just looking at a vertical, simply supported beam. Right? So it's going to move. Not only is it going to move, well, the internal member itself between nodes is going to displace, right? So we've got this, what we would call big delta, right? And then we've got this little delta. Elias, welcome. Kind of chilly out there for you? Had to wait for it to warm up or what?
There was an accident on Wilson.
Oh, really?
Tesla got murked.
Damn.
Yeah, and it seemed like, I don't know, I feel like normally you could just roll it out of the way, but maybe it was off or broken. It was stuck right in the middle of Wilson.
Really?
Everybody delay.
I wonder if that has to do with like the electric motors, right?
Because I've seen like a video of them trying to
Yeah.
tow those things, and they have to like,
Because some of them are all-wheel drive and
Yeah.
stuff, so I mean,
So-
and there's a motor on every wheel, so I wonder if it's like dead in the water, you gotta
they've
pick it
had
up.
issues with that.
Yeah. Alright, well, thanks for the story.
Alright.
So we have P big delta and P little delta, right? So when we were looking at the homework, we were looking at this big delta, right? The global displacements. Well, if we look at local displacements, right? The moment in that member is going to be amplified by the fact that the member displaces, right? If we looked at a free body diagram there, it's essentially an eccentric load acting on this member. In VA, it will do your P big delta, right? You clicked on the P delta analysis button. It's going through and doing the geometric stiffness matrix, right? Does it account for this little delta? No, it doesn't. How do you think you would model this in order to capture P little delta? Knowing how the finite element, what's that?
Add more nodes.
Yeah, fuck yeah, Greg. Way to go, buddy. Right? Add more nodes. You split this up into like 10 members. Now visual analysis is looking at, okay, where is that node at? What is the geometric stiffness, right? The softening effect of the fact that as this member moves and displaces, right, we're gonna take into account the fact that that axial force over some displacement is going to change the overall stiffness, right? It's gonna make it softer. It's gonna want to displace more because we're adding more load to it, right? More internal strain energy. Right? And so in VA, if you wanted to capture P little delta, you would need to split up your member into multiple members, right? And they talk about it in the help file and how you would do that, okay? So, but typically, right, if we're not looking at, say, a stability condition and looking at P delta effects, right, we normally can just model members as one member, right? Top to bottom.
So does that also mean like self-weight doesn't get taken into account into P delta effects?
Correct, because it's only calculating those effects. I mean, it's doing P big delta if you click the button, right? Because it's gonna say, okay,
Self-weight wouldn't.
it
go
would
into that.
self-weight, yeah, would self-weight move this node at the top? No, right? So it's not going to affect it, right? But
That P little delta comes from like forces like I guess, that's still, yeah, all the forces.
yeah. I mean, self-weight does influence P big delta because it's, well, yeah, because it's gonna take it and VA is gonna take that load, it's gonna do energy equivalent forces, it's gonna put them at the ends, right? Figure out what our displacements are. It knows now, free body diagram, it knows that the displacement's there, right? And so it takes into account that as this thing moves over, overall globally, the self-weight's moving over, right? It's taking part of that uniform load and it's putting it at that node. And so that does get incorporated into the geometric stiffness matrix, right? For the self-weight of our column that we looked at in the homework. All right. So that's one example of something where you would probably want to split up a member, even though we don't technically have like 10 members sitting between one column, right, and another column. Another one would be in a lateral model where we have a diaphragm, right? And we might want to have the plate elements connected at more than just the ends of a member, right? If we had, here we go. Aaron's not gonna get this. This is where,
Oh, Aaron's in building.
wow. Hopefully it's, well, I wonder what the roads are like. Right? So if we had a diaphragm, right? We had brace frames here and here, and we put a plate element, right? One single bay, does something like this, we connect it. We have some load acting on it. What's the problem with this? Is there a problem with this? If I loaded a single bay, right, this is looking at plan view, say the second floor of a building that looks like this, right, we got columns, we got beams, say we put brace frame through here. Put some line load acting on the edge, right, we're gonna push this thing over. I put one plate element.
Are the brace frames also connected at the nodes?
Yep, so it'll be connected here and here. Maybe if I say it this way, I want to design this beam right here. Which would be this guy here. this guy here. Would this be an okay model?
I feel like the diaphragm doesn't transfer the load in the beams. If you want-
Correct.
If you want to send the beam. Yeah.
Yep, exactly, Daniel. So like, if I was looking at this beam, right, the diaphragm is only gonna be able to push here and push here, right, where the nodes of my plate are connected. And so if I was really designing this beam, it's only gonna see maybe, well, it depends if these are just tension only or compression and tension braces, but it might not see any forces, right, from the diaphragm. And we would design it saying it has no axial force in it, right? And so that's another condition where you might want to consider breaking up a member into multiple segments.
It's still receiving the energy equivalent amount, though, right?
What's that?
Like half of that load is going to each of those nodes, or like.
Yeah, but
or I
is the
guess-
beam gonna see it though? The beam wouldn't see any of
It's gonna
that
see
one.
the portion of it, right? The energy equivalent portion of each node.
No, because it's not applied to the actual member, it's in the node. So if we look at load path wise, right, it's gonna go into the diaphragm,
Yeah.
it's going to be supported essentially by these two
Just
brace
like
frames,
all
right, it's
these
gonna
nodes.
displace like this. And when it displaces like this, the only connectivity is at these two nodes. And if we look at stiffness, right, if these were compression and tension braces, that force is just gonna run straight down, right? It's gonna be a big tension force and a compression force on this guy. Does that make sense, Liz? Yes, Brandon?
There's a, you put a plate on top,
Mhm.
would you have to make the plates smaller as well with however many, like?
Yeah, so like, again, you could split this member up, right, and that was the problem with, like, Adam came in and talked about that building where the guys put, or the designers put plates on the roofs, right, and all the walls, and they didn't interconnect it with all the rafters, right, so if we just put one big plate, one big rectangular plate on here, and these were the nodes for that plate, it has no idea that there's a beam here that might add stiffness. Right, and so yeah, you would have to do something, well, you'd really wanna break this up even more.
You'd also have to split up the beam though, right?
Yep.
You couldn't just split up the plate, that wouldn't make any difference.
You'd have to do something like this, right? And then obviously you'd have to continue that on. Something like that. Cause now, when this thing moves that force into here, right, now this plate can apply that force along this member. Right? And so those are some scenarios where you would want to maybe split up this beam member, right, in an effort not to model the beam, but to model the load path and how that load is getting into the beam or into the lateral system, right? All right. So typically, right,
Split a beam up like that, can you still show like the full shear moment diagrams for like all the connected members, or how would that work?
yeah, so what VA will allow you to do is you can actually combine a member. So you could split it up into discrete members, but then you can go through and you can just combine the entire thing and make it look like one big member. And then, yeah, it has internal nodes, which is calculating what's going on there, but it looks at it as one member. So then you would click on this one member and you could report that member and look at the moment and shear diagram across the entire member.
I think also if you highlight every one and then click like. the
Yes,
shear moment
it'll
diagram.
combine them. The one thing you have to be careful with doing that is if you drew them in opposite directions, then you can get these weird jumps in the diagram, because in the diagram, it's going from the first end of the member to the second. But if you had, this was say positive X for this member, and this was positive X for this member, the local coordinates, that's where things get a little tricky, because then it's going to, when it goes through and it finds, okay, this is the shear diagram for this member, I'm going to start at the positive, or at the, X equal to 0, the local coordinate beginning of this member, gonna go to the end, then I'm gonna go to the beginning of the next member, to its end, beginning to end, beginning to end. And so if your local coordinates are flipped around, you can get these weird jumps in that diagram. That's where when you combine them, it's nice, because then it says, okay, this is all one member, the local coordinates are all aligned, you'll start at one end, you'll work your way to the other. That would be my only caution, okay? Usually what will happen is you'll draw this one member, right? And then you decide to, you'll right click on it, or you're up in the ribbon, you'll say, I wanna split this member. It'll ask you, how do you wanna split it? You can do it in fractions and lengths, number of pieces. And when you do that, obviously if you start with one member and it has a local axis direction, when you split it, it's going to keep that in the same direction. It just gets weird when you start drawing things differently and you say you wanna draw this way, and then you happen to draw that way. Okay. All right. So diaphragms and P delta are some examples are special cases, right? Or we might want to add additional members in order to model it appropriately to capture our load path is really what we're looking for, okay? So that was for beams and columns. Now when we start looking at walls, floors, foundations, maybe even we could talk about plates, right? Connections, steel connections, right? In this case, the indeterminacy of elements require a lot of extra thought on our layout. Right. Stiffness attracts load. So the second we start having a lot of indeterminacy, a lot of different load paths, right, we can start really manipulating and changing the way that the load is going to be flowing through our structure. Okay? So we got to really start thinking about it when we look at walls, floors, foundations. Really, when we start looking at plate elements, we can easily overwhelm our software in pursuit of an accurate model. Right? Accurate in quotes here. Right. When we start modeling continuous things, plates, right, whether it's walls, floors, foundations, right? I showed you in VA how you can take an area and auto mesh it, right? You guys can't do that in the educational version. Well, in an effort to say, okay, I know that I'm gonna get better convergence or a closer solution to the converged solution if I increase the number of elements, right? You could easily just click on an area for a diaphragm and say, and make the plate element super, super small, right? And it'd be really easy to model 100,000 plates for, say, the floor in Roberts Hall that we're standing on, right? It'd be really easy. Well, it's really, really easy then to overwhelm our software because it's not, like when you talk about 100,000 plates, right? There's a lot of degrees of freedom, right? That stiffness matrix is massive, okay? And so it's really easy to do that and we gotta be careful not to. So we say that refinement becomes large part of discretizing. Right? In this example here, we got on the board, right? So we have a single bay, right? 2 brace frames, maybe in the other direction is moment frames, right? We know that it might be a benefit, would be a benefit, to maybe split this beam up and add some connectivity between the beam and the diaphragm so that the load going in and out of the diaphragm, right, follows a load path that it would follow in the mathematical model, right? Simplification from the real world. But we'd probably have studs that are sitting on the top of this beam that are dragging load in and out, right? This is gonna be designed as a beam in the special brace frame. We've got beams, if we had multiple bays, maybe we had beams behind it and in front of it. You guys have done special concentric brace frame design now, right? In steel?
Still doing it.
What? Okay? When you do this, right, there's one crazy ass check they make you do is constrained axis, flexural torsional buckling. It's a pain in the ass, all right? But it has to do with the fact that this section might want to twist. Got a stud sitting on here. You have a huge axial load going into this member, right? Massive axial load going into this member to try and get these guys to RYFYG, right? And so we did this large axial load. Well, this member, right, we have lateral torsional buckling. Well, in this case, it's called constrained axis flexural torsional buckling because it's constrained at the top flange, right? It's got some restraint for rotation, but the bottom it doesn't. So this bottom flange wants to roll over, and we got to check that. And so in order to check that, we need to know the axial load in all these members, right? Well, I want to know how this axial load actually comes in, so I'm going to split up this member into multiple members, right? Well, you can see if we started here, well, maybe I want to, instead of having this 20-foot long beam and now I only put load in, right? The nodes are only at, say, 4 foot on center, or in this case, 5 foot on center, right? There's 4 plates. I want to make this coming in at 1 foot on center. I want to know what's going on every foot, because every foot I've got a stud, right? So then you put one, you have 20 nodes here. You can imagine if I have 20 nodes and I want to keep this grid going on, right? Now I got a shitload of plates in order to keep this going on, right? So then that's where we start. Triangular plates are nice for refinement because you can, get larger with our mesh, right? We can split this. Now we've got 2 there, but we only got 1 out here, right? And so we start really fine around the beams and then we work our way out, right? And so that's where refinement becomes a large part of discretizing, because we wouldn't really want to, if we're looking at this one bay, probably okay. But if we were looking at norm, right, engineering building, you couldn't just grab that entire diaphragm and want to split it up into 50,000 plates, right? It's going to overwhelm things. So you're going to have a lot of this going on, and when you do that, right? Yeah, so you start really starting to hone down. Well, and then on this side, you're going to want to do something similar, right? Work your way out. So like out in the field out in the field, where your diaphragm's acting like this huge deep beam and you're not really super worried about what's going on out there, you don't have as many plates. But then as you get closer to, well, I'm really interested in how that load is coming in, maybe even per foot on this member, right? So then you have a ton of nodes, right? So then you get this weird mesh pattern, and everywhere that you say have a drag or somewhere that you're pulling load in and out of the diaphragm, you've got a lot more discretization, a lot more splits. And then out in the field where you're not really as worried about it, right? You're gonna have it be larger, because if you were to just, what's that?
You could go back to rectangles.
You could go back to rectangles, yeah. Yep.
Because those are just almond triangles themselves.
They are 4 almond triangles, yep. Yep. They are.
If you do the auto mesh thing for like the diaphragm,
Yep.
will that add a bunch of nodes onto your beam that's connected?
It automatically does some of that. Well, no, so it doesn't, it won't create nodes along your member if the member doesn't have nodes in it, right? It's only gonna connect to nodes that are there.
So you'd wanna put all the nodes on the beam that you want and then hit
Yep.
auto mesh. and
So
then-
you could hit auto mesh, you could look at the discretization, right? And it would not put nodes right there. I mean, it might put nodes in it, but it wouldn't be connected to the beam. That makes sense, right? So they would just be free floating nodes that are connected to the plate, but they're not connected to the beam. In order to get it connected to the beam, then you could jump over here, select the beam, split the beam, and then if auto meshing, it would just remesh this area knowing now that they have coincident nodes, and it would make that connection,
Okay.
right? Yes. So refinement's a huge part. And as we've done right here, right, just kind of talking through this one bay problem, it really comes down to more focus on load path. And our results of interest. which leads to more plates. At a lot of those places that we just talked about, right? Connections with other elements. We didn't really talk about this, but load sources, right? Or supports. For a while there, VA didn't have the ability to load the edge of an area or edge of a plate. So what we would do is we would take a member, like a beam, we would put it in here, right? We'd split it up so that the plate was connected to it, and then our beams allow us to put in uniform loads on them, right? And so if we made this beam super, super flexible, right, so that it didn't affect the stiffness of the diaphragm, then we could take this beam, right, and use it as a tool to transfer load into the diaphragm. Does that make sense, right? We split this guy up to a bunch of nodes so that all these plates are connected to those nodes, and if we put a line load or a uniform load on this beam, that beam is going to transfer that load into these nodes, into this diaphragm, right? So there's ways in which you can get around some of the limitations by just looking at and thinking about the idea of, well, what's the load path? What's the behavior that I'm trying to capture, right? How does the finite element process work, right? With respect to the relationships between these nodes and our assumed shape functions, right? Our assumed field variable functions. How does it split things up? How does it behave? And we can implement things. Now you can load sides of stuff.
When adding a beam like that, that's super flexible, do you just go as tiny, like a 1 inch squared, like?
Yeah, we did
wood
something
strip,
really, really
or-
small.
Or would it like, can you go too small to where it like I mean, cause there's probably huge deflections.
It depends.
Better.
Yeah, it depends on,
Cause it's just
The-
to transfer load.
yes, so like it depends on the distances between your members, right? I mean, it wouldn't take a whole lot of, you don't really have to try and get a member that's gonna do this, right? All the way through and be that flexible, because if you look at the diaphragm as a whole, this whole thing is a beam, right? And so when it displaces, it's super, super stiff. And so really all you're trying to do is get the load into each one of these nodes.
Yeah, so it doesn't matter that it's doing
Yeah. But if you had a thinner area, right, or a thinner diaphragm right here, you wouldn't really want to use like a W30 by something, right?
Right.
Because then that stiffness would start affecting things. And it might start spanning this whole distance, and it might start putting more load on these nodes, but in reality, you want to actually put it out here. So. Okay. So load sources or supports, discontinuities. Right, when you have holes in diaphragms, which architects are really good about doing. For some reason, they think stairwells are super important, okay? So if they put stairwells or openings in your diaphragm, obviously, if you have a load that's acting, right, so say we put this hole in the center of this. Norm was a good example of one where they just had to have a freestanding 3-story tall atrium inside the building. It's like, oh man, you're really, really messing us up here. Like, this isn't fun. All right. So you got this big hole. Obviously, when you're applying load either on one end or the other of this diaphragm, right, it's got to transfer around depending on where your lateral system is, right? If you just had, say, a brace frame right here and you applied load here, it's got to go into this diaphragm. This diaphragm is going to deflect, right? It's going to transfer that load. It's going to come to either side of this, and then it's got to go back into it. So obviously, when we're making those transitions, right, we're essentially moving the force vectors within this, or stress vectors within this diaphragm around these discontinuities. We might want to put more refinement around there to make sure that it has the adequate flexibility, right? We're modeling it appropriately to capture that behavior going around and what that does, right? Re-entry corners are really tough, right? Because we have a really abrupt geometry change here. And so you can imagine as this thing opens up, right, we get a lot of rotations, we can get some really high stresses there. okay? And as we know from our Ullman triangle, we can have linear strain distribution, but we can only make that transition over the plate area, right? So if we had a plate that was connecting to that corner, and that plate, say this was 10 feet, and that plate went 5 feet over, right? The stress difference between here and here is gonna be significant, right? And so you're gonna get this huge gradient of stress change from the point at the re-entrant corner to one of the points at the plate, right? And so in order to minimize that huge distance or difference, right? Because we're gonna need to know these values out here. We're gonna design the diaphragm for that. So we're gonna really wanna maybe break this up even further so that when it's calculating the stiffness matrix and all the stresses and strains in each of these elements, right? There isn't this huge differential over which it's calculating, right? We can make that smaller, and that goes back to discretization, making sure we converge, right? And so we might want to add some additional members, right, where we have discontinuities in an effort to capture some of that behavior, right? Big thing here, right? Start simple. And we want to step into complexity. And I think Adam said it a couple times, right? I mean, and that's why we started with that homework with the cantilever is starting simple, right? Understanding what exactly you're doing, what the model's doing, how you load things, the results you get out of it, right? You need to understand the basis before you start just jumping into this. You might say, okay, yeah, I need to discretize this, I need to do this. Well, maybe you do the bare minimum. Maybe you don't even connect this member. You do one big, oh fuck, I'm gonna have to erase the whole thing, huh? Right, you do one big plate element, right? Make sure the model runs first, right? Once the model runs, then you can start refining it and changing things. And maybe you start by you're designing that beam, and maybe when you're designing the beam, you refine it one way, and then you go and you're designing the diaphragm, you refine it in a different way, right? And you're changing it and you're adjusting the model just to make sure that you're getting the behavior that you were expecting out of your mathematical model in your VA model, okay? Right, and so all of this comes back to, I'm going to show you here. Right, this is norm, architectural model, massive, a lot of elements, right? Curtain walls, tons of brick, right? Glazing, steel stud walls everywhere, sheathing, insulation, mechanical and electrical equipment, right? Everything going on. This is our architectural model, right? This is the street view from Grant. Okay.
Is that a utility?
That's a utilidor, yep. Yep, it comes out right outside those entry doors that you walk into in the front there. Goes underneath the street and heads to the sub. And if you see from the other side, we had to give them a stub out.
No, it doesn't go anywhere.
Doesn't go anywhere. But the next time they build a building out to the south, then they'll have something.
Or they take like another parking lot.
Yep, they have another parking lot, build another parking garage. Right. Has anybody seen the master plan for the, yes, Dan?
Yeah, so I'm trying to think something. If you're modeling, let's say, diaphragm, right? And then a beam, and it just happened that, let's say your diaphragm has maybe, let's say 3 nodes, maybe in the side of the beam.
Yep.
And then your beam has maybe 4 nodes and they don't coincide with the diaphragm. I think, do you mean that the diaphragm is not going to see, I mean the beam is not going to see the diaphragm, right?
Correct.
Okay, so it means like.
They have to be coincident, right?
Okay,
They
yeah.
have to land at the same, it has to be connected at the same node.
Okay.
You go in VA, it'll say node 13.
So you have
right?
to make sure everything.
Yeah, you can click on that plate, that diaphragm plate, and it'll tell you what the 3 nodes or 4 nodes that make up that plate are. And you would have to make sure that that's at node 13, right? Then you go over to the beam, and you click on that beam, right? It's going to have its node, yep. And you would make sure that that also says node 13. And then you would have the connectivity, right? Something that maybe a little faster than that is you run the model, right? You can look at displacements. We're gonna talk about troubleshooting, right? displacements are huge. It's a huge ability to make sure or understand how the compatibility of the model is set up. And if that beam deflects, right, and that node moves, and then the plate does not move, the plate is not connected, right? There has to be compatibility at nodes. Okay, that's always part of the game. So.
What were you saying about master plan?
Oh, they're doing some bridge over. They're in the master plan for the athletics thing. There's like a huge indoor practice facility that's going to go into the field, the big intramural fields over there. And then they got like a sky bridge that goes across Kagi.
That was our capstone project.
Oh, really? Yeah.
We didn't do that.
Oh, you didn't? Oh, okay. Yeah, this is master plan.
It was too expensive, they wanted to change that.
Did they?
Yeah.
We'll see. I mean, they always like the pretty pictures. My brother-in-law is the managing partner in Bozeman for A&E, and they did the engineering building, and they also did the master plan stuff. And they always say that they shoot for the stars when they do all that shit, because when they go to donors, they want to show them like, oh man, look at this, we got a fucking sky bridge. This is gonna be sick. Or like recruiting, it's a huge tool. Like, hey, look at this. Like, this is where we're headed, right? Be a part of our program, and you might be able to have this practice facility, right? Or
That's what they told us too, like our first semester we did this like really pretty awesome thing, and then
Yep.
the second semester we just like made it super simple.
you got realistic.
Yeah, exactly.
Yeah, that's real. Okay, so that is our architectural model, right? So we went from this massive thing, right? All of those elements, and we put inside of it this skeleton, and this is the structural model, Revit model, right? That we devised that incorporates all the structural elements in Norm. Right? So you can see we're making a huge jump just there. Right? Us as structural engineers make this huge jump. I mean, if you looked at Norm right now, you'd be lying to say that this is the only thing that resists loads in that building, right? We make huge simplifications. We're saying that none of the architectural components on that building play a role in the lateral stiffness. We ignore it all. This is what we look at as structural engineers, right? Even though there's tons of interior walls in here, right? Continuity between diaphragms, jit board on both sides of them. There's mechanical systems laid out throughout the entire thing, right? Just all sorts of elements that are acting with respect to resisting loads, but we're gonna ignore them. We make this simplification, right? Then we have this simplification. This is our interpretation of the real world as structural engineers. And then we take this and now we make find an element model out of it, right? So this is we ignore. There's not a single interior wall in this entire building, right? But that means there's gonna be a huge amount of stiffness in there, right? That's gonna contribute to the overall performance of the building, right? So we ignore all of that. This is the back side of it, right? And then from there, we do this with it, right? Pretty close to that model that we just looked at, right? I mean, we get a column member for every column member. We have a beam member for every beam member, right? You don't see, if you look at this bay, right? So this is our diaphragm level. We have our joists, we have our girders, we have areas that are spanning between, right? One-way action, we're assuming we're putting concrete on metal deck. It's gonna span this direction, it comes out here, right? We have all these nodes that are connected at floor levels, right? Some of the things that we don't have in this model, right?
And then we did the round concrete.
Look at all that extra shit on the side of the building, right? These little guys were a pain in my ass, right? These are what hold up the brick, okay? They're cantilevered HSS members that go and they attach to each one of the columns, right? And they're applied, they run across the entire front and back and sides of the building because we couldn't hold enough brick. There's code requirements as to how far you can go with brick freestanding, right? So we had to adjust for that. The other thing is they have lots of glazing, right? And so we ended up having to carry a lot of brick over the top. Well, that's in the real world, but if you look at the model, right, none of that shit's there. Right?
Did you really have to do any designing for that round room for like Jean Forte?
The one in the ground,
Yeah.
this one?
Yeah, it's just like, since it's on the ground, you just kind of.
Yeah, it's just a big slab and grade.
That's just stepped.
Yep. Kind of felt bad it took them a lot of pours to make that happen.
I was gonna say like.
Martel was in there a long time, like, Let's pour a ring. Okay, let's pour a ring. And then on top of that, you know, there's tons of electrical stuff that goes in there for, you know, all the audio video stuff.
So not really structural design, but just a lot of other design.
No, the slab on grades, I'd say, is like, I think it's dumb. I think it's incredibly stupid that they rely on us to design something. It's non-structural, right? You could pull the slab out of this whole building, right? And it wouldn't affect the performance of the building at all. It's not tied into anything. All it is just sitting there on the floor, right? Then they go and they polish it, right? So the architects want to polish it and make it look all fancy. It's cracked as shit. I don't know if you guys walked around in there, right? Okay, and that's always a gamble with concrete. But again, they for some reason rely on us, the structural engineer, to tell them how to do that. And it's like, that's an architectural finish. I've gotten arguments with architects about it. It's like, I don't want to do that. It's not on me, right? But then everyone's just like, oh, structural engineer, his fault. It's cracking to shit, right?
How is that not structural?
It's
There's
not
like a
connected.
basement- There's like a basement below it,
Not
and
on
like.
that
So the
part.
basement is down here,
Yeah, that's the other end.
right? Those are retaining walls. This is concrete on metal deck that covers the top of it, right? But all these footings, all these spread footings that are throughout the floor level in this building, right? They don't rely on the slab for anything.
Then isn't there drilled piers for parts of this?
Yeah, not drilled piers. They are engineered aggregate piers,
Yeah.
EAPs.
Right.
So what do they? Yeah, rammed earth essentially. So what they do is they take a big drill bit, they drill into the ground, and then they start adding in different material. And when they add in like structural fill, like something with a nice gradation, they throw it in there, they tamp it down, they put it up in lifts, okay? And it's weird. So then you end up getting all of these like nice, beautiful, like 4 foot or 3 foot diameter circles, right? And we tell them, hey, we're gonna have a spread footing on the corner of this building, right? Where you walk in the door across from the sub, there's a spread footing underneath that corner, and then we told them, hey, we need 6,000 pounds per square foot underneath this footing. This footing is gonna be about 6 foot square. So then they go through and they design, okay, we need to do two foot diameter engineered aggregate piers. Or we just do 1 4 foot diameter. And they decide how deep they go, they decide the material they put in there, they decide how many lifts they put in there. And when it's all said and done, then we can just design it like a spread footing. Otherwise, this building would have to have been on like deep foundations.
Yeah, that's what I was gonna say.
Right?
I knew what you were saying.
EPS, or I guess it's Barnard now, right, is half of the building is on deep foundation piles, the other half is on spread footings.
Is it ever not conservative to, like, you just took out all that stuff that's adding stiffness on the inside, but would that ever, like, not be okay to do?
I
Like,
mean,
what's-
potentially, I guess I can't think of a
Like-
case right off the top of my head, but I can't think of one.
When you
That's
assume
it.
it'll pass, but then it actually transfers because of that stuff, or like.
Yeah.
Yeah, there's definitely definitely something to like think about, right? When you're discretizing and you're making these jumps from architectural model, structural model, mathematical model, and then our VA model, right? Making all those jumps and simplifications, it's like, ooh, should I incorporate that? How would you incorporate that? If you do incorporate it, would you like want to make sure you detail those walls then, right? Because when they go and put them in, they're using the architect's plans for how to fasten the bottom track, right? Or the bottom sill plate and top track to the diaphragms, right? They might only put a pin like a powder actuated fastener in the tracks, like once every 4 foot, once every 3 foot. That's not a lot of load transfer, right? So maybe it wouldn't do it, right? I mean, the other bad thing about gypsum board is it's, very brittle. So you push it one way, it cracks, then you turn around and try and push it the other way, and your stiffness goes way, way down, right? It degrades really quickly. And so again, it's like, okay, in a seismic condition, maybe we can't rely on it because this building's doing this, right? And those walls are just like cracking to shit and they're not gonna contribute. Wind loading, maybe? I don't know. Yeah, it's a decision you'd have to make. I mean, in residential construction, we use gypboard walls all the time, right? I don't know if you guys designed a residential house at all. You guys have, right? Have you done gypboard shear walls? Yeah. You probably did prescriptive like IRC stuff,
Yeah.
braised wall panel stuff, right? Yeah. So you can use gypboard in those conditions, but you get in the commercial world and the IBC, and it gets a little tougher to do stuff like that. So, but I mean, it's a good question to think about and like ask yourself, like, how much load will this transfer? Should I really incorporate it? If I do incorporate it, I should probably think about how I detail it and make sure that the contractor's putting things in there that allow it to transfer load, how you want it to transfer load, right? Without being overwhelming.
Is it kind of like considered when you're like ASC or someone comes up with like a damping coefficient for a building though? When you're applying seismic loads, like isn't that kind of considered like, yeah, your building's gonna have a
Yeah, I mean,
damping coefficient because we realize all this is in here.
yeah, so when you calculate your natural period and stuff like that, like your, the prescriptive methods for calculating like frequencies and stuff, yeah, there's an assumed somewhere around like 5% damping.
And they
in your
kind of
building.
consider all the other stuff in there.
They do, right? So in that case, it's like,
It's like we kind of
are
know
you,
it's there.
yeah, for sure, but then are you counting it for strength? No, right? So it works as a shock absorber, like a shock absorber in your car, and it's going to dissipate that energy so that it just doesn't perpetually just rock back and forth. But is it really transferring load? I don't know. And degrading, which absorbs energy, which makes it so that when this thing shakes, when it's done shaking, it will stop shaking, right? But yeah, no, I mean, it's definitely in some areas of the code because someone was like, shit, there are a lot of walls in this building. It is going to affect the performance of the building. You should incorporate that. Right? There's things like in ASC's, in the dead load chapter, talking about like the provisions for partitions and whether or not you incorporate it in your structure or you don't, and how much load you should incorporate. Right? There's like a line, like sometimes we do like a mechanical electrical allowance, right? Well, if your building meets certain criteria, they make you do, I think it's 5 pounds per square foot for partitions. Right? If your building has any ability in the future use to rearrange walls, they're saying you have to incorporate the load associated with moving all these walls. Right? So we make this huge simplification. Right? And then we make this model out of it. You can see we're not looking at, right, we pinned all of the columns at the base, right? That's a huge simplification. Right? Mentioned we left out some components that we designed by hand, some of those ledgers that held up some of the brick walls and stuff like that, right? Throughout this model, we put hinges in the members, right? Beams, potentially columns, braces up here at that clear story, very top up there.
So, a lot of those nodes at the bottom are fixed for rotation, like
In some
against
direction.
one direction.
Yeah, I was thinking the same thing, but not the other.
But they wouldn't be, like, would this maybe be just for designing the lateral system for one direction, like an event going this way, and then maybe they.
It's like, why is
So
one
the-
fixed?
so
Somewhere that fixed
Norm is a
rotation.
moment frame building,
Yeah.
okay? So this is a moment frame in Norm. If you walked in, this is the entryway across from the sub, right? There's a 2-bay moment frame. So this bay has resistance to rotation, right? Fixed base, right? So it has resistance to rotation in the strong axis of this frame, right? Whereas this is a gravity column. It has no strong axis or weak axis rotation restraint, right? But it does have restraint in the global twisting direction. Why does it have that? Because up here, we have a beam that we're attaching with shear tabs, and we're assuming it has no resistance to weak axis rotation, right? If you click on this beam and you say it's simply, where's that? Yeah, this beam, and you did simple support, right? It releases the weak axis and strong axis bending at the ends of this member. Well, if you release the weak axis and strong axis bending of all 3 members attached to this guy, this node can twist, right, with this member. So if you do not restrain this vertical rotation, the twisting of this column, then this column is unstable, right? It has.
And you do assume that with the foundation, like the spread footing, that it resists that also?
Yep, that it would resist that. Yep. Well, there really shouldn't be any load going to it, right?
Yeah.
But it's a mode in the, like, in the derivation of the stiffness matrix that has no stiffness in it, right? And so there's an instability there, okay? So we gotta make sure we restrain it adequately so that it can't just do something, right?
That's from
but there wouldn't be any really load on
There
them.
wouldn't be any load, but there also, so there would be resistance, but there's also not load.
Agreed. Right. But on this one, right, we're not going to make these simply supported. These are connected at the end rigidly. And so this column can't twist, right, because it's fixed on each end by that beam. I'd say that's a very common instability that you can find in models.
What do all the green nodes mean? Yeah, it's also.
I think those are vertices, and I don't know why only some of them are showing up.
Maybe just the zoom.
Yeah, true. So in plates, instead of areas, instead of creating nodes, they have vertices. So that's essentially their nodes. And so you can move the location of the vertices.
Can you get the actual model on your computer if you're not?
I could have Chris send it to me.
Actually, like zoom around. and
Yeah.
stuff.
It's just, it is massive,
That's what I
right?
was wondering if
So that was
you could
another
bog
thing.
down, switch to
Yeah,
views or
so that's another thing is, right, in our simplification, because we were going to overwhelm the software, we were overwhelming the software, we split this into two models, right? This might be I think this is our gravity model, but then our lateral model is separate from this, right? So that we could analyze this for just lateral forces, right? So in here, I don't think any of these are actually just areas. We actually didn't give it any stiffness in our diaphragm. So all we're doing is using the areas to separate loads so that these members, right, these joists and girders, get line loads on them. Because there's a lot of members in this building that were not influenced by lateral loads, right? They're out in the field, they're not transferring things, right? They're not this cord or collector, it's not dragging load anywhere. And so we essentially made a model, designed all of those. And then when we did the lateral model, well, then we had to pull results out of this model, pull results out of the lateral model, put them together so we could actually design members, right? Where things had gravity and lateral on them. All right, we are moving so damn slow, but that's okay.
So